Hello students, welcome to this video lecture on the paper Analog and Digital Electronics. This is the paper for BTech third semester Computer Science and Engineering students. The subject code of which is ESC 301. Today I am going to discuss on counters, which is the continuation of my previous lecture on counters. Myself, Gaur Gopal Jana, Assistant Professor, Department of Electronics and Communication Engineering, Header Kolkata College of Engineering and Management. In my today's lecture, there will be asynchronous counters with mod number less than 2 to the power n. Okay. And after that, the asynchronous down counter, particularly 3-bit or mod 8 binary down counter will be discussed, and after that the cascading of asynchronous counters will be discussed. So students, let us go to the topic. Divided by n ripple counter or asynchronous counter with mod number less than 2 to the power n. Okay. Counters can also be designed to have number of states in their sequence which are less than 2 to the power n. The resulting sequence is called truncated sequence. To obtain the truncated sequence, it is necessary to force the counter to recycle before going through all its normal states. Okay. Now whenever we want to count to a base n which is not power of 2, then we have to consider divided by factor, which is the same as the modulus as discussed earlier. Okay, so these counters are called divided by n counters. The basic counter is modified to produce the required mod numbers which are less than 2 to the power n by allowing the counter to skip states that are not part of the counting sequence. Okay, one of the most common method for doing this is by making all flip-flops to reset after count n with the feedback gate okay, in the circuit. Now what is the design procedure of divided by n ripple counter? That is, first we have to determine the number of flip-flops required to design a counter. Okay, then we connect these flip-flops as a ripple counter, and after that we have to find the binary representation of this capital N, that is mod number, which mod number counter I have to design. Okay, now we have to connect all the flip-flops output and that are 1 at the count n of the counter as an input to the NAND gate. Okay, connect the NAND gate output to the clear inputs of all flip-flop. So by this procedure we can design a mod n or divided by n ripple counter. Okay, and for an example, this is an divided by n ripple counter. We have to determine the counter sequence which is the modulus number. So this is the first flip-flop. So A is the LS bit and C is the MS bit as a counting sequence. Now the output from flip-flop second and third flip-flop, that is BC, is connected to the input to the 2-input NAND gate. So when both the outputs of flip flop, that is B and C, is high, then only output will be 0, which resets or clear the all flip flops at its and force to back to its initial state, that is 0 0 0. So when both the inputs B, C is high, then only these resets of flip flop occurs. Therefore, the counting sequence will be 0 0 0 to 1 0 1, that is 6 states. Therefore, you may call this region divided by 6 ripple counter or mod 6 count. So this is the timing diagram of this mod 6 counter, that is counting sequence will start from 0 0 0 0, and when the output will be 1 1 1 0, it will force to back to its initial state, that is 0 0 0. Okay, so this is the mod 6 counter. This is the state diagram of mod 6 counter. If we assume a starting count of 0 0 0, the diagram shows that the state of the counter change normally until it counts 1 0 1. When the next clock pulse occur, the counter temporarily goes to 1 1 0 count before going to the stable 0 0 0 count. Okay, here we can see the 1 1 1 state is never reached. Okay, not even temporarily. Therefore, this is the mod 6 ripple counter. Okay, in this logic diagram we can see the inputs to the NAND gate are the outputs of the flip flop B and C. So the NAND gate output is low when B and C both are equal to 1. Okay, until the NAND gate output is high, which does not affect the clear input of any flip flop. So this condition will occur when the counter goes from 1 0 1 state to 1 1 0 state. Okay, the low signal at the NAND gate output will immediately clear the counter to 0 0 0. Okay, the counter goes to 1 1 0 state. It remains there for a few nanoseconds and before it recycles to 0 0 0 state. Thus we can say that this counter counts from 0 0 0 to 1 0 1 and then recycles to 0 0 0. Okay, it essentially skips 1 1 0 and 1 1 1 state, so that it goes through only 6 different sequences, that is 0 0 0 to 1 0 1 state. Thus it is called mod 6 counter or divided by 6 counter. Okay, this is another example, that is mod 10 ripple counter or decade counter. Also we can say BCD counter. Okay, so a decimal counter follows a sequence of 10 states and returns to 0 after the count 9. Okay, the counters with 10 states in their sequence are called decade counter. A counter with a count sequence of 0, that is 0 0 0 0 through 9, that is 1 0 0 1, is called BCD counter also, because it has 10 states. Sequence is the BCD code. Okay, so this is the logic diagram of 4-bit asynchronous decade counter with 4 JK flip-flop. When the counter goes count 1 0 1 0, the NAND gate output will goes low and all the flip-flops are clear condition. Okay, thus when 10th clock pulse occur, the counter output Q, that is DCBA, will be 0 0 0 0 instead of 1 0 1 0. Okay, now this is the timing diagram of mod 10 ripple counter. Here we notice that the NAND gate output goes low to clear all the flip-flops when the counter becomes 1 0 1 0 1 0. Okay, this is the temporary state. So any mod n counter can be obtained by changing the NAND gate inputs. Okay, asynchronous down counter. So far we have discussed with the up counters, that is count upwards from 0 to maximum values. It is possible to make a down counter by modifying the up counters in some ways. Okay, in down counter it counts downwards from maximum value to 0 and repeat. Okay, so this is an example of 3-bit binary down counter. 3-bit means mod 8 down counter. Okay, here the modification done by connecting one flip-flop complementary output to the clock input of the next flip-flop. Okay, so this is an up counter. Here the clock input is the regular output, normal output of the previous flip-flop, and so on. And this, if we do the modification of this up counter such that the clock input of the next flip-flop is the output, complementary output of the previous output, and so on. In this way we can convert a up counter to down counter. Okay, so this is a 3-bit down counter logic diagram, and here this is a state diagram which counts downward, that is 1 1 1 is the maximum, and 1 1 0 1 0 1. So counting is downwards, and it will reaches at 0 0 0, and after that it repeats the same sequence. Okay, and this is the timing diagram. Here also all the JK flip-flops are in toggle mode connection. So when a clock input in negative S trigger is applied, then initially if the all outputs are in reset state, then after applying the clock pulse, all the flip-flops will change its output. So all outputs will be 1 1 1, and then again when we apply a clock input, then the first flip-flop output will change its output, which have no effect in the next flip-flops. So again when we apply another clock pulse to the first flip flop, it will again change its regular output, which at the same time the complementary output changes its time, and which will change the output of the second flip flop, and so on. So by this timing diagram we can see that starting from 111, after that this Q2, actually this Q2 is the MS bit. Okay, so 111, 110, 101, 100, 011, and it reaches at 000, and again if we apply the clock input, then it will be 111. So in this way the this counter is counts downwards, okay, descending order. Okay, so apart from this, another another two modifying state will be such that by making the flip flop trigger on PGT instead of NGT, means positive going S trigger. If we make the flip flop trigger input as positive going S trigger in place of a negative going S trigger, then a up counter may working as a down counter. Okay, and another one is by making the counter output Q bar, that is if we take the counter output from complementary outputs, then we may get the down counting sequence. Okay, so in this three modification of up counter, we can get the down counter. Ripple counter or asynchronous counter can be connected in cascade to increase the modulus of the counter. Okay, a mod M counter and mod N counter is cascade to give mod Mn counter, means here is an example, that is this is a mod 4 counter and this is a mod 8 counter. If we cascade these two, then we can get the mod 32 counter. Okay, 4 into 8, that is 34. So mod 34 counter can be achieved by cascading two counter. One is mod 4 and another one is mod 8 counter. So larger asynchronous or ripple counter can be constructed by cascading smaller ripple counters, connect last stage output of one counter to the clock input of the next counter, so as to achieve higher modulus operation. Okay, so we can get the higher modulus counter by cascading to lower count sequence counter. Okay, it is another example of a higher order counter by cascading to lower order counter, that is cascading 3-bit binary counter, means mod 8 counter, and also it is a mod 8 counter. By cascading these two, 8 into 8 means 64. So mod 64 counter can be constructed using these two 3-bit counters. Okay. If counter is not binary counter, requires additional output, means a mod 100 counter using to decade counter. So this is the modulus counter which is not exactly the 2 to the power n sequence. So this also can be achieved by cascading of mod number counter, that is here it is an decade counter, and which is cascade with another decade counter to achieve mod 100 counter. Okay, these are the references used in this video lecture. If you have any question regarding the topic discussed to today's lecture, you can contact me through this email IDs mentioned here. Okay, so students, thank you for now. Have a nice day.